Welcome to the 16th session in the second module of the course Signals and Systems. We've been talking a lot of geometry in the last few sessions. So, let's take the following example. We have a periodic signal xt, a square wave. I'll show one period of the signal. The signal is 1 for the interval 0 to t by 2 and minus 1 for the interval t by 2 to t, and this is one period. And needless to say, x t plus t is equal to x t for all t. So, it is periodic with period capital T. Now, we find out its decomposition at different frequencies. So, let us take first the zero frequency component. The zero frequency component is essentially the mean of x t over a period. And as you can see, that mean is equal to 0 for this x t. That's because you can see that the function is symmetric about its middle, as positive on one side of the middle of the period as it is negative on the other side. So, the area under the function in one period is 0, and therefore, there is no so called DC component, there is no constant component. Now, let us take the kth component. So, the kth angular frequency that we need to consider is 2 pi by t times k, and we shall evaluate the two components at this frequency. The first component is of course xt dot product with cos 2 pi by t kt multiplied by 1 by t cos 2 pi by t plus the inner product of xt with sin 2 pi by t kt and then again multiplied by 1 by t sin 2 pi by t. Now, let us visualize how we are going to calculate each of these dot products. I will show them to you in two different colors. I will show this dot product to you first in red. Take one period, dot product over a period, don't forget. This is x, and I draw cos. How does cos 2 pi by t kt look? So, it is going to complete k cycles over a period of t. So, between 0 and t by 2, it is going to complete k half cycles. And between t by 2 and t, it is again going to complete k half cycles. How would this? Let us take for example k equal to 1. So, it would look like this. You see cosine begins like goes there and then rises up. This is k equal. Let me draw k equal to 2 as well, but in dotted. So, it is completed 2 cycles as you see over the entire period of t. Now, you see you can carry this forward. You can look at k equal to 1, you can look at k equal to 2, I have already drawn them for you. You can look at k equal to 3, and in each case you will see that whatever area is contributed on the positive side is annulled by the negative side. Let us look at these two cases to convince ourselves. So, let us look at the k equal to 1. This part is integrated out to get a total of 0 area, because whatever positive area is contributed from this portion is annulled by the negative area contributed by this, and similarly whatever positive area is contributed by this portion is annulled by the negative area contributed by this portion. So, therefore, for k equal to 1 the dot product is 0. The same thing holds for k equal to 2. You can see that whatever positive area is contributed by this portion is annulled by the area contributed by this, and so too by these two. Now, you can visualize this. You see, I have shown you the situation for k equal to 1 and k equal to 2. I encourage you to do it for arbitrary k. So, what I am saying is the dot product with cos 2 pi by t kt falls to 0 for whatever positive integer k you take. So, let us record that. So, what we are saying is this dot product or this inner product equal to 0 for all positive k. So, we should now only focus on the second term, and let us do that. Let us focus only on the second. Let us therefore calculate the dot product. In fact, that is also easy to do. I will show it to you graphically. I have xt here. I will show you for k equal to 1. You have sin 2 pi by t kt. I will show that in green. So, sin 2 pi by t kt has an appearance like this. You can see that this dot product is definitely non-zero. And in fact, this inner product can be seen to be 2 times what you get on each half cycle. So, this is from 0 to t by 2 and this is from t by 2 to t, whatever you would get between 0 and t by 2 would be the same as what you get between t by 2 and t, because positive multiplies positive here and negative multiplies negative on this. So, 2 times the integral from 0 to t by 2 xt sine 2 pi by t times t. You are talking about k equal to 1. And of course, xt is equal to 1 for that interval. So, what do we have here? Very simple. We have 2 times 0 to t by 2 sine 2 pi by t t dt, and that is minus evaluated. So, minus 2 cos 2 pi by t small t divided by 2 pi by t evaluated from 0 to t by 2. That is minus 2 by 2 pi by t. Of course, cos 2 pi by t times t by 2 minus cos of 0, and that gives us minus t by pi times minus, that is easy to evaluate, and therefore that is minus 2t by pi. So, this is the component for k equal to 1. Now, let me draw for k equal to 3 and you will see the pattern. So, let me first show you the sketch. With k equal to 3, you are going to have 3 full cycles. So, of course, you had 1 half cycle and of course, another half cycle, and you see now in the other case you had just 1. Now, here you need to have 3. Well, let me instead draw for k equal to 2, that might be easier to understand. So, here, so for k equal to 2, I need to have 2 full cycles. How will 2 full cycles look like? You are going to have 1 cycle completed between 0 and t by 2, and 1 more full cycle completed between t by 2 and t, 2 full cycles. And you can see that the inner product is going to be 0. Why is this true? Because whatever, you can see that in each individual half cycle, an entire cycle of the sinusoid has been integrated out. In fact, you can see this will happen for all even values of t. You are going to have a 0 integral because each half cycle is going to integrate out full cycles, complete cycles. For example, for k equal to 4, you would integrate out 2 cycles in the first half interval and 2 cycles in the second half. For k equal to 2, you are integrating out 1 cycle in the first half interval and 1 cycle in the second. And similarly, you can go on constructing this. So, for all k equal to even, you are going to have a 0 component. That is very interesting. There are no cosine components, there are no even components. So, what is left is only the odd components, k equal to 3, k equal to 5, k equal to 7 and so on. And of course, you can see that there is always going to be a symmetry. For k equal to 3, for example, you can construct the first half cycle, look at the inner product, if you focus on that first half cycle, and you will see it is the same as contributed by the second half cycle. But what we will do is, so as to avoid any confusion, we will just write down the inner product as it is. So, I will write that down for you. So, for k odd, we have the inner product is 0 to t by 2 integrated 1 multiplied by sine 2 pi by t kt dt plus integral from t by 2 to t minus 1 into sine 2 pi by t kt dt. And let us evaluate each of these terms separately. Now, I leave it to you to show that this term and this term are equal. Exercise. Show these are equal. This one and this one. And therefore, I am just going to evaluate any one of them. Let us evaluate 0 to t by 2 sine 2 pi by t kt dt and multiply it by 2. And I leave it to you to work this out. It is essentially going to be 1 by k times the answer for k equal to 1. So, we had this answer for k equal to 1, 2t by pi for k equal to 1. We will just divide it by. So, this is now 2t by pi into 1 by k. I leave it to you to verify this. And all in all, what we have is xt is therefore summation k going from 1 to infinity 2t by pi into 2k minus 1 sine. This is the complete expansion. I leave it to you as an exercise to verify this. So, I worked out one example. I suggest you work out a few more. We will discuss a few more examples, just presenting them as exercises to you, but you must work them out on your own. Thank you.